into the graphing portion, we have a few things to talk about with logs. And the one thing when I'm teaching or introducing logs in Algebra 2, the one thing I really stress to my Algebra 2 students is, what is a logarithm, right? So like, how can you make sense of it later? It says notes 3.2, log functions in their graphs. It's been up there for at least a minute. So no. A log is really just an exponent. It's really important that you understand when you see logs out in the math world, what are we referring to? And something that can be challenging for a lot of people when they first learn logs is like, what the heck does this mean, right? So you've really got to like just buckle down and be like the mathematicians. This is just something they made up to say how they were undoing exponents. You know, like every operation has an inverse operation. Addition has subtraction. Multiplication has division. A square has a square root. Okay, all of those things. And raising an exponent to a variable needs an inverse operation. That is the log. So the log is just how we write that. There is a log base 10. It's called the common log, but that is not equal to. Oh, okay. Okay, so I have three statements up here. Log base 4 of 16 equals 2, log base 3 of 81 equals 4, and log base 9 of 3 equals 1/2. And I like to sometimes just look at these logarithmic statements that are already written out for me and use them to help me comprehend what a log actually means, right? So can anybody rewrite the first equation in exponential form? Owen? 4 squared equals 16. Okay, so you maybe just know the definition of a log, and then you can rewrite it in the correct place, or I call it like my swirl method, where I start at the base, I go around the equal sign to pick up my exponent, and then I come back in, and that's my answer. Okay. But the key piece here is, notice that the answer to the log, the thing that the log is equal to, the 2, that is your exponent in the rewrite. Okay. So then we could easily rewrite the next two statements, right? The second one would read 3 to the 4th equals 81. Remember, the thing that the log equals is actually the exponent in the exponential expression. And 9 to the 1/2 equals 3. 1/2 is the exponent. This is a good review of exponents for us. What does it mean when you raise 9 to the 1/2? You're really just taking the square root of 9. So you learned this in your rational functions unit, that the root is in the denominator. So that will be helpful for things like, like Kyle asked this question about that number 25 on the homework assignment. But you know about negative exponents will flip things, so make them fractions or turn them back into non-fractions. Whole number exponents will just like multiply it by itself a certain number of times. If you use a fraction exponent, your denominator is going to be your root. So you can take different roots of numbers. So that would be helpful. Okay. And so kind of going along with that, now we understand, okay, so logs are just ways to rewrite exponential expressions, but when we see a log and we evaluating a log, we're finding an exponent. So now we're going to write this in our notes, log base 5 of 1/25th, and silently on your own, take a few moments to digest and see if you could figure out what the answer to that log is. Remembering that the answer is the exponent. Okay, so think about rewriting like we did on the left. You don't know what the exponent is. You'd like to know the exponent. Can you come up with a number? So I'll give you a little bit of time to think. You had a little bit of time to come up with some ideas. Have a quick chat with your table groups. What do you think that exponent is that is the answer to the log?
Because then that makes it 1 over 5 squared. Oh, 5 Never mind.
Okay, let's come together. This is my little thought bubble right here. So when I see something like log base 5 of 1/25, this is what's going on in my brain. You can see. I'm Miss Crumpy's head right now. Yep. I think. What is my base? 5. 5 to what exponent will turn into 1 over 25? I'm rewriting it in exponential form, but the exponent is unknown to me. So then what exponent do I want? In order to make it into a fraction, I need a negative. To change it from 5 to 25, it needs to be squared, so negative 2. Okay, so you're saying 5 to the negative 2 equals 1 over 25. If I run through this, that's 1 over 5 squared, flip it, which is 1 over 25. So sure enough, it worked. Okay, so just remember, when you're answering a log expression, you're trying to find the exponent that works. However you see that or you think about it, as long as you're answering the exponent. Okay. Next up, we're going to talk about some properties. Oh wait, I think first the definition of a log comes up, then some properties. Okay, so this is just like the definition of an exponential function. Okay, yesterday we said f of x equals a to the x. Well, now we're talking about f of x equals log base a of x. And what I have written there in red, that's how you read that. So you don't have to say log little a. You just say log base a of x. That's how we read that. I mentioned before that the log was really the thing that like undid the variable exponent. It's like the inverse operation. So the log function is the inverse of f of x equals a to the x. And so if you look back at your notes from yesterday, you'll see some of these same notes about a, the base. The base has to be greater than 0. So never will you ever have a log with a negative base. Okay? Always has to be positive or not 0. And a can be equal to 1. Remember we talked about yesterday in the exponential function, 1 to the x is a really boring function. It's actually constant. So your base isn't going to equal 1 at any point. It's got to be greater than 0 and not equal to 1. And then this statement is really like the definition of a log, kind of what we were working with on the previous slide. Y equals log base a of x. If you were to rewrite that, start at your base, a to the y, go around the equal sign, is equal to x. So then y is your exponent, right? So it's just saying the exponent is the answer to the log. Okay, so that's just kind of like the mathematical definition of that. Okay, now before we graph, we are going to review a few properties because we're going to use some of these properties to help us in our graphs. Make table of values that are really easy to evaluate. So there are 4 of them on the screen. We're going to do other properties of logs tomorrow that you may remember from Algebra 2. And there are 4 of them, and we've got blanks there, so we're going to try to fill in the blanks. Log base a of 1 is equal to something. Log base a of a is equal to something else. The third one, that's probably the weirdest one. It's got a lot of stuff going on in it. It's the inverse property. So if you use what you know about inverse operations, that might be helpful. And then the last one says log base a of x equals log base a of y if and only if. So I got my IFF there. So before we spoil everything and tell you what the answers are, we want to give you some time to kind of see if you can fill in the blanks. what was happening in my head when I was evaluating that log, like log base 5 of 1/25th, I'm searching for the exponent. Okay, and that'll help you in the first two, and then you gotta think outside for 3 and 4 for what may be happening. So if you want to talk with your groups, you can do that. See if you can fill in any of those blanks. Argue for what it is.
Dividing log A.
How much equals? That's what I was asking you, not to read it out again.
I don't know.
First one's 0, next one's 0,
Yeah.
What?
Wait a few seconds.
No, you were not. Second one?
6.3 log inverse.
Okay.
B of log B of x equals x. Equals x.
The last one I started.
Second part of the third.
Yeah.
X.
Gives you the x doesn't equal the log of x.
The log is the log.
Seven A is a B for some reason.
Like that's an exponent. It's a log base A of x.
Let's come together and see where we're at.
A for log base A is 1.
Okay, log base A of 1. Elise, did your group come up with an answer?
No.
For the first one? Did you come up with one for the second one?
Yeah, we said one.
Oh, okay. So I'll accept that. Oops. Okay, log base A of A is equal to 1, and I think you could argue, because you're thinking about your base, this says because. Okay, so you're thinking about your base A to what exponent equals A? Well, the answer must be 1. A to the first is equal to A. So I think you could use the same logic on the first statement. Ethan, did your group come up with an answer to the first one?
We got
0. So you're thinking about A to what exponent equals 1? Well, anything raised to the 0 exponent is equal to 1. So you're actually going to see those two. I'm always going to use those in my table of values on my graph. I'm going to always go back to the parent graph for a log like I did for exponentials, like I just graphed 2 to the x or 3 to the x. So I'm always going to graph like log base 2 of x, log base 3 of x. And I'm always going to choose for my x's 1 and a, whatever the base is, and 1. And then I'll always get out 0 and 1 for y. So that would be really easy for me to evaluate. Okay, any groups think they got an answer to the 2 blanks in the third property? What does the inverse property do, Tristan? It's just x. You know, I mentioned while you guys were jotting these down, I said, think about just inverse operations. What do? They undo each other, like plus 5 minus 5 cancels out. Okay. Now, you could also think about this like setup. Remember, this is base A, so you're thinking about A to what exponent equals the thing that's behind the log, a to the x. Well, it must be a to the x. Okay, so it's equal to x. And then over here, this one is just the reverse of that. It's written in exponential form. So if you wanted to evaluate it, like your base is a, so you would really write it as log base a, and then of something equals whatever the exponent is, which is log base a of x. Oh, that came out funny. I moved my thing, so that should be a sub a, right? Okay, that got moved when I dragged it. But then the only way those things would be equal is if it's x. So both of them are x. Now, you might need a little bit more time to look at the inverse property and make sense of that. By all means, when you go home tonight, you can pull out your notebook and just kind of look at that and try some numbers and see why that works. Or just take us for our word that this inverse property is equal to x. Whatever is most helpful to you. Okay, Okay, and the last one. Log base a of x is equal to log base a of y if and only if was true. X equals y, Emily says. Yep. So this is our one-to-one property. It's a lot like the one-to-one property for exponents. If the logs have the same base, then the only way they're going to be equal to each other is if you're taking the log of the same thing. Okay, so you can use that to solve some equations. Okay, now we're going to get into graphing, okay? Everybody looked so excited there. That was great. Smiles around the room.
Notebooks like
Yeah,
they're
that's fine.
required.
Okay, f of x equals log base 2 of x. Now, I'm actually going to take a little side stroll here. You don't have to do this for every graph. But I'm just going to talk really quickly from yesterday about f of x equals 2 to the x. So, when I did the exponential function for 2 to the x, I found 3 points. -1, 1/2, 0, 1, and 1, 2. And my graph looked something like that and had a horizontal asymptote at y equals 0. So this was -1/2, -1, 1/2. -1, 1/2. This was 0, 1, and this point was 1, 2. You can look back in your notes from yesterday and see that graph, right? Now, I've already said this a few times, but the log is the thing that undoes the exponent, right? So it's its inverse function. Let's take a little trip down memory lane to chapter 1. What is true about inverse functions? Their graphs, their equations, their tables. How do you find inverse functions? Flip what? Switch x and y. Okay. So just knowing my graph from yesterday, I could essentially make a graph of this log base 2 of x because that's its inverse by switching x and y. So if I switch x and y right here on this point, -1, 1/2, instead I'd be going 1/2 to the right and 1 down. Maybe I'll do this one in blue. Okay, so that's 1/2 -1. Instead of 0, 1, it would be 1, 0. And instead of 1, 2, it'll be 2, 1. And if I'm switching x and y, notice that my horizontal asymptote is y equals 0. If I'm graphing something logarithmic, the x and the y are going to switch, so now it's going to be, instead of y equals 0, it's going to be, no, I'm switching x and y. Instead of y equals 0, it's going to be x equals 0, which is what kind of line? Vertical line. You're going to have a vertical asymptote. Okay, so now I have a vertical asymptote at x equals 0. And this is the graph of the logarithmic function. Oops, that looks like a y. It's an x. So some things for us to think about is when you're identifying things here for your logarithmic function to help you graph, one of those things that you could find is a vertical asymptote right away. If there's no kind of shifting, then your vertical asymptote is always going to be at x equals 0. Okay, so I'm going to mark that down right away. Now, if there's shifting left or right, just like when we shifted up and down in an exponential function, the horizontal asymptote changed. If we shift our whole graph left or right, then our vertical asymptote is going to change. So now you'll have to pay careful attention to your h value in these functions. Your vertical asymptote is going to be like basically x equals h, your right or left shift. So if you say left 4, then your vertical asymptote is now at x equals -4. Whatever that may be. Okay, so that's going to be helpful to me. So I'm going to put my vertical asymptote down on my graph. That's at the y-axis. And then I'm going to go ahead and make a table of values. And remember I said I was going to use the properties from that previous slide. So if I flip back to that previous slide, I'm going to use these top two properties. I'm doing log base 2 of 1, which will be 0 for y, and then I'll do log base 2 of 2, which is 1 for y. So I'm going to put in 1 and 2 for x. And the log base 2 of 1 is 0, and the log base 2 of 2 is 1. Essentially, in my table of values, oops, trying to write log. If this is log base a of x, I'm always going to put in 1 and a, the base, and I'm always going to get out 0 and 1. That's going to be easy for me. And I can plot these 2 points, 1, 0, and 2, 1. Now, we kind of know, because we looked at that exponential function, we kind of know what the log graph then looks like, right? On this left side of these 2 points, it's going to drop and get really close to my vertical asymptote. And then on this right side, it's going to be increasing. It just doesn't increase very fast. So kind of looks more like a square root function, except for it doesn't have a start point. There's my log graph. So I'm really using my vertical asymptote and a couple of points to make a good log graph. Now I can fill in the answers. What's the domain? 0 to infinity. What's your range? Negative infinity to infinity. If you look back at this f of x equals 2 to the x from yesterday, those things are flipped, right? But that makes sense because we're switching x and y, so our domain and range got switched. Okay, so now you'll always have restriction to your domain, but your range will be all real numbers. X-intercept. In this one, we have our x-intercept on our graph, right? So we could just label that point it is 1, 0. How would you, if you didn't have your x-intercept, how would you be able to find the x-intercept always? You're saying something about 0. Tristan, what about 0?
You plug 0 in.
For y. So we would say 0 equals log base 2 of x. And then if your log is all by itself, you could just basically rewrite it in exponential form. That's 2 to the 0 equals x. So x equals 1. So then my x-intercept is at 1, 0. So if I didn't have it on my graph, I could find it. Okay. And is this graph increasing or decreasing? Increasing. Now, we have a restricted domain, so we'll say it's increasing from 0 to infinity over its domain, but it is never decreasing. Questions, concerns? Where did I get that? What did I do? Things that you want to ask. Yes, Emily.
Increasing from, like, how come increasing is the domain and not the range? Isn't it increasing that from the bottom?
So we're talking about where left and right is your graph increasing or decreasing. So just kind of as a review from chapter 1, if you have like a absolute value graph, it's increasing on, it's decreasing over here on the left. Let's say that my axis of symmetry was x equals 2, and it's increasing on the right. Okay, but notice that like if you use like, let's say this point was like 2, 3. If you said like 3 to infinity for increasing, you're telling me like min to max, but like over here you can't say 3 to infinity, and you can't say negative infinity to 3. So you're really talking left and right. Anything else? Yes, Nick. So I was doing an aside about the exponential function from yesterday.
Yeah.
Okay. But we agreed that like if the horizontal asymptote is y equals 0 and we switch x and y, then for this like parent graph of a log, it's always going to be at x equals 0 because that one would always have a y equals 0. The other way you could think about it is if you try to think about in your head, so here's my thought, log base 2 of 0, then you're thinking about 2 to what exponent equals 0. Now we argued yesterday doesn't exist, right? So then there is no answer to that, so that's where your vertical asymptote pops in. You also can't do negatives, like you can't do log base 2 of negative 2. No exponent turns it into a negative. A negative exponent So you have to have like a,
Zero fract.
what's that?
So it's not like having a zero fract,
Yeah, I mean, as the functions change, that number will change. But yeah, it's whatever, it can't be 0 behind the log.
Yeah.
Okay. Good question. Anything else? Okay, now let's do one with some shifting, right? So we're going to do f of x equals log base 2 of x minus 3. And I'm thinking about, like, if I'm studying and prepping for, like, what I need to show on a graph of a log, basically you're going to be using your vertical asymptote and you're going to be using a couple of points. Okay? And then that's usually enough for you to say what the graph of the log will look like. So we have f of x equals log base 2 of x minus 3. Now, I certainly could attempt a table with this actual function, but it's probably going to be easiest if in your table you use the parent function. So I'm just, again, if I'm doing log base 2 of x, I'm going to put in 1 and 2, and that'll give me 0 and 1 by the properties of logs that we discussed earlier. I already have those points. And then I'm just going to use my transformation. Since this is x minus 3 in parentheses, what direction is my graph moving? Right 3. Okay, so I'm going to move those things right 3. I'll go ahead and plot those points 1, 0, and 2, 1. And then to make my actual graph, I'm going to move them right 3. So I'll be at 4, 0. And 5, 1.
For the x minus 3,
Mhm.
so would it always be in parentheses if it's
Yes. If it's meant to be a left or a right. If I wrote it like log base 2 x minus 3 with no parentheses, I would assume that was down 3. Okay, good. What else shifts right? Besides the points? The asymptote. Okay, so we're going to draw our asymptote now at x equals 3. So got that down. And then I have what I need. If you want to find some other points in the table, you can, and then shift those points as well. But 2 points is really all I expect to see on your graph. And that should be enough for you to know what the graph looks like. That logarithmic function could be like flipped, reflected if you had a negative in front. Okay, so then it would come down through the 2 points if you saw that the points were going down instead of up. What would we say for domain now? 3 to infinity. Range would be negative infinity to infinity. X-intercept? 4, 0. And this one is increasing from 3 to infinity with no decreasing. Now, on the next slide, we're not going to graph this one, but I'm going to do an example where if I had made a table, if I did shift them, then I wouldn't have my x-axis or my x-intercept on the x-axis anymore. So I'll show you how you can find the x-intercept without knowing it on your graph. Like here, we could just look and say, oh, it's 4, 0, right? Okay. If you don't see your exact x-intercept, then we can still find it. Anybody got any questions on this guy before we leave? Okay. So if I graphed log base 2 of x, which I already have done a couple of times, and if I move it right 1 and up 2, I'll have shifted those 2 points so that neither of the 2 points, the original points, lie on the x-axis anymore. So if I'm asked about x-intercept, I don't want to just guess it on my x-axis. I want to actually figure out what that is. So then I would do like we did on that first one, set y equal to 0. So 0 equals 2 minus log base 2 of x minus 1. How would you solve for x in this equation? Minus 2 from both sides first, so anything that's added or subtracted, move it over. That's negative 2 equals negative log base 2 of x minus 1. Then you would divide by negative 1. You want that log to be positive. Okay, so that's going to be positive 2 equals log base 2 of x minus 1. And now do you see how you got the log all by itself? Okay, log base 2 of x minus 1. So now you can rewrite it in exponential form. The base is 2, the exponent is 2, so 2 squared equals x minus 1 and add 1 to both sides, so x equals 5. So we know that the x-intercept should be at 5, 0. So I may still ask you about x-intercepts, and if you use my method of like the table of values and shifting, your x-intercept may no longer be on the x-axis. Like you may not have a point there, but then you can solve for it. Okay, last thing, just really quickly, we won't take a whole lot of time here. You will have some questions on your homework assignment that have natural logs in them. So Nick had asked a question about log base 10. That's actually the common log. The natural log of x is log base e, right? So it has the base e. This one you would do in your calculators. So I would just go to my y equals menu. And I'm going to pull up my calculator so you can see. I'll go to my y equals menu. And I'll just type in the natural log of x. This time I don't want e, right? Just hit natural log. And if there's other numbers, just type in all the other numbers. And then go to second graph to get my table. And you probably want to go searching in your table for the moment you find the errors, because that means that your vertical asymptote is right there, right? Okay. So you know your vertical asymptote is at x equals 0. I could plot a few points after that and have a nice graph of a natural log. Okay. Now, if that graph has been shifted, you might have to search in your table for the errors where your vertical asymptote is. But other than that, it's going to look like another logarithmic function. Okay. I'll do like I did today. Tomorrow, I'll show you the answers to the homework assignment at the beginning of class. So make sure you're doing those graphs and you're being thoughtful. Check your x-intercepts, your domains, so that you can see if you get those right on your homework.